There we go. All right. What's this? Nice. Okay, so you got your test back. Maybe better than you thought you did? Yeah. Nice. Okay. I'll start by doing this because this is how I figure out which video it is. So if I have to wait too long. 006. There we go. Okay. So I don't want you to be freaking out about this test. First of all, it was a weird test, right? There's a lot of stuff going on, a lot of things that we had to cover and get through. Okay. Like I've been saying, from now on, it kind of gets more cohesive and put together, right? So it's like, oh, we got to scramble all this together for test one, and then things kind of settle down and into a rhythm. Okay. Might not feel like it to you guys. For me, it feels like that. Okay. So, yeah. Oh, no question. I'm on high alert. Okay, so test one, kind of peculiar, right? It will come back on the final, but not as much as test 2 or 3, okay? So it will come back to haunt you, but not really. Okay? And remember my policy that if you do better on the final than any of the tests, I'll just put that test weight on the final exam. So if you think you can do better on the final than you did on this test, who cares, right? You can forget about this test. Focus on test 2, test 3, and the final, right? So I never want you to feel defeated because you had a bad test. I'm going to say it. This test wasn't that good for anyone, okay? So, and that's okay. We're moving forward, okay? Let's talk about a little bit about how I mark stuff, okay? You all start with 100%, and then things come kind of decreasing down, okay? So I don't go through and I add up marks. I take away marks for errors, okay? So if you feel like something's weird, and sometimes, you know, it's on a question like the first one out of 10, if there's really a lot of stuff missing, I'll just say -6, and if you need me to justify it, then fine. But I will be posting the solutions, so you can have a look through the solutions first. Oh, there we go. Okay, so I'll post the solutions. Okay, back in business. So you'll have them. You're sharing your screen. Great. Okay. All right. So usually I always try to follow through with your logic, your reasoning. And so I wrote a lot of illegal math out there. There's a lot of illegal math going on. So you want to try to nip that in the bud, right? Because that's going to come back to haunt you, right? So really figure out what went wrong there, right? And took marks off, right? Yeah.
On the solution, you're going to show how you get there?
Oh yeah, it's my handwritten solutions, like every step, more than probably you need. Okay. Yeah. So, and you'll see a lot of okays. Okays are like, okay, or okay, or okay. So it's a pretty flexible marking thing that I have. So for marking, okay, which usually just ends up being like a red scribble. It means that something went wrong, right? And it's not worth taking marks off of because it's so minor, or your procedure was right, but you are using a value that was wrong. right? So you followed through and everything's okay, right? But just so that you know that you didn't do it right, you have to still go back and check it out, right? But as far as following through and the procedure goes, you're okay, right? So that's usually what's going on is I say, okay, sure, yeah. Okay, so means you followed through, usually. You followed through with the right procedure using wrong numbers, usually. That's often what it is, okay? Or just minor errors that aren't gonna affect anything. Okay, so the okay, if you have a question about an okay, sometimes I get carried away with my check marks, so you'll see a check mark, and then I'll actually look at it and go, oh, it's actually, no, something went wrong here. Okay. Whenever you see a minus a half, that's just half a mark off. It's not 1 out of 2 marks. It's just half a mark off. Half mark off. Right? Because that could get confusing, right? If it meant taking 1 out of 2 marks off or half a mark, kind of a big difference. Right? What else? Any others out there? I didn't do any on this test, but there are rare occurrences of a capital Y in brackets. What is that? It's a thumbs up emoji. Come on, guys. Yes. It's from like the MSN days where we had to type out our emojis. Yeah. So the rare thumbs up. It's very rare. I don't throw them out for anyone. Okay. It has to be either really funny or really clever to get a Y in brackets. Now you know what you're aspiring to. Okay. So, all right. Any other kind of weird marking stuff going on out there? Oh, be careful. I wrote that a lot, right? So be careful. It just means that I saw a lot of kind of discombobulated calculations. So it's like, oh, I'm gonna do this here. Oh, but I need this. And then I'm supposed to kind of follow around here, right? And so be careful, or, you didn't know how to keep a negative somewhere. Be careful. So be careful just means everything's good, right? Everything's kind of there. You just have to be more careful, right? And I think I put some be more deliberate in showing your work, okay? And that just, so I want to see your thought process, right? Because that's what I'm marking, right? And so I want to see, okay, so I want to get from this point to this point, and I want to see how you take me there, okay? I don't want to have to decipher all this, all these weird calculations, although sometimes they pan out, art marks, okay? So be careful, just look back and see what happened, but yeah.
I got reasoning too. Does that mean something?
Yeah, so your reasoning, so exactly, so I was really chatty on yours, huh? So if I'm asking for your reasoning or show your logic, right, again, you can't just plug stuff into a formula right away, right? I want to see, well, which formula are you using initially, right? Because I saw a lot of people just jump right into plugging into a formula, right? I want to see, okay, I'm going to use this formula, and then you can plug it in, and then just kind of follow through with the logic and the reasoning. So even if you can't show me mathematically, it's worth something writing it out in words, right? And so, for example, for the shutdown point, right? If you had said, because I asked, what's the shutdown point? Even if you got nowhere in part A, what is the shutdown point, guys? It's when the price of what you're selling, right? You can't charge more than what it costs you to produce it, right? And so just telling me that, that's showing me that you know something, right? And that's worth marks, okay? Probably only half a mark in this case because you had to know that it costs you $3.50 or $4.50 depending on your version, right? There are 2 versions of the test, of course. You'll know by knowing if the special instructions has a colon or no colon after. I like to keep it secret, keep it safe for the first test. So, okay. So, that's my marking, right? You start with 100 and then I dock marks. So there are some kind of free marks in there often. Yeah. But yeah, if you do have questions, then just let me know and we can look at it. Any questions before we start part 3? No? Okay.
What was the
Yeah.
highest grade?
In this section, I want to say 42 out of 44. Pretty good, right? I know, no 44 out of 44s. What, you can't do that. You can't have a test. Well, there was always someone who got 100% on each of the questions. So if there was ever a question where no one was able to get 100%, yeah, then I'll adjust things. But I'm tough like that, okay? Any other questions? No? All right. So today we start fresh, part 3. And we're finally talking about simple and compound interest. We're going to start with simple interest, right? Looking at your formula sheets, they're split up, right? Simple interest here, tiny, tiny, and then we'll move into compound interest and then annuities. We are starting on page, they don't have numbers, 90-ish. Yeah. So simple and compound interest. So this is where we get to shed test 1, new skin, okay? And so of course, just like before, we have to establish some general rules. So we're going to talk about exponents and logarithms. Just how do we deal with those? What are some of the rules associated with those things? And from now on, after we introduce them, right, I'll expect you to know how to apply them and use them, okay? But we'll talk about them. Okay. So section 4.1 is vaguely called the basics. I think, again, I feel like the first section of every chapter is called the basics. But can't confirm. So the first thing that we're going to talk about is exponents. Exponents are powers, if you'd like. We've already actually dealt with exponents, but now we're going to look at them more closely. Okay. There weren't any on the test, but we've already kind of seen how do we deal with them. Okay, so exponents are used if you have a situation like a times a times a times da 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 times a, right? Just multiplying a series of n a's, right? So let's say there's n of them. We love this general notation. Okay, so then we would write, well, that's the same as a to the power of n. Right? So a to the power of n is just saying you have a multiplied n times. Okay? So we need to know the ins and outs of exponents first. Okay. So where a is the base, okay. So a is the base and n is the power. Is the power, or exponent if you'd like. So we have a base and an exponent, right, or power. Okay. And just in words, a to the power of n is n a's multiplied together. Okay. So for example, if we have 5 times 5 times 5 times 5, we can rewrite that as 5 is our base, right? 5 to the power of, we have 1, 2, 3, 4 5s. Right. Just kind of quicker. What if I said 2 to the power of 5? If you had to write it out. Well, now 2 is our base, and we have 2 multiplied by itself 5 times. So that's the same as 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5. 5's too many. Okay. So I think we're all on board so far. Okay. Let's talk about the rules of exponents. And if you need to refer to them, they're on page 92. Whenever we're working in math or in stats, we always have to kind of state our assumptions first, right? And so, for example, a is the base, n is the power, right? That would be an assumption that we made. Okay, so the first thing that we're going to do is we're going to let a be greater than 0. Okay. What does this mean? It means that the base, right, a, has to be a non-zero positive number. Okay. So the base must be a non-zero positive number. Here's where the textbook gets a little rude. M and N are in the set of real numbers. It's like a fancy R. Yeah, it's kind of it's in the set. So I'll do it big. It's a round E. It doesn't matter. I'll tell you what it means, right? Because a lot of math is just kind of knowing what it means. You don't have to pay too much attention to it. Okay, you just look at it and say, oh, it's in the set of real numbers. What does that mean? Oh, it means all the numbers. Okay, so it's in the set of, and it looks like that, real numbers. So how we read this, I'll just put it in quotes. It means that M and N are in the set of real numbers. And I think the problem is that, I mean, Joe, my boss, but even myself, we kind of become numb to this kind of notation. But I know you probably haven't seen it before, right? Unless you're probably taking calculus, maybe. Okay. But there's lots of that notation. You can kind of ignore it. Okay. It just means that m and n are in the set of real numbers. What are the real numbers? Real numbers are any numbers that you can think of, right? From negative infinity to positive infinity. So the set of real numbers, is any number between negative infinity and positive infinity. Okay. So really what it's saying is that m and n can have any value, right? Any value that we can think of is in the set of real numbers. Okay. It's kind of weird notation, right? But I want to show it to you because it comes up in the textbook and don't want you to be thrown off. Okay. All right. We ready for some facts? We've already kind of seen some of these. Okay. So the rules. Here are the rules that we're going to play by. So, because math is just the game. A to the power of n, we'll start slow. A to the power of n is a times a times a times a. Or we already established that, but it's a multiplied n times. Second rule, which we already saw, you've probably forgotten though. A to the m times a to the n, we can rewrite, that's the same as a to the power of m plus n, right? So you can move back and forth between either of these, right? Say you want to combine your powers, right? As long as you have the same base, right? We can combine our powers by adding them together. Or other way, right? If you have a power or a base here and you have two things added together, then you can split them up and say, well, I can break off one times a to the other. So we'll be able to move back and forth as we need to. Okay. So this one says, if multiplying powers of the same base, we can simplify by adding the exponents. We can simplify by adding the exponents. So that's me. I just want to see. Oh yeah, I'm writing out these little explanations because if you're looking at the textbook, it only lists the math rules, not the explanations, right? So you'll probably want to have the written explanations, right? We assume that you can read this. I know that's not necessarily true, so okay. I just wanted to check. Okay, so that's our second rule, which we've already used. Can't remember when, but same idea. If you have a to the power of m over a to the power of n, we still have the same base, right? they're both base a, and that's important. We can rewrite it as a to the power of m minus n. Right, so if you're multiplying the same base, you add the powers. If you're dividing the same base, you subtract the lower one from the top one. Yeah? So if dividing powers of the same base, oh, I was going to say we add them. We can simplify by subtracting the exponents. But it has to be in that order, right? The top exponent minus the bottom one. Okay. Any questions so far? I'll just, yeah. You have to remember them. I know. So we'll want to do some practice probably. Yeah. Okay. So I'll make some, leave a space. It got so cramped. Rule number 4, if you have something like a to the m in brackets to the power of n, that's like a to the power of m multiplied n times, but a to the power of m is a times a times a, m times. Yowzas, right? So this is the same as a to the power of m times n. And I just think of it as they're essentially on the same level there, right? A to the power of m to the power of n. So you can just multiply them. Okay. And this is just an extension of rule number 1. Right? You can treat a to the power of m as your base. Right? And then bring the n inside. How about if we have something like a times b to the power of m? So now we have 2 bases, base a and base b. And they're to the power of m. What we can do when we're multiplying inside the brackets, okay, is we can just bring in the power and it attaches to each of the bases, right? Same thing, we can pull them out and have it just the common power. Okay. So we can rewrite this as a to the power of m times b to the power of m. Yeah. But sometimes we'll want to use this fact that it distributes evenly onto both of them, or if we have to pull out a power, more likely. So it's going to happen. But yeah, you totally can. So if multiplying 2 bases, the power expands inside onto both bases. The power expands inside to both bases. Right, so if you have to break out the brackets there, right, expand them, then you can bring in that power and just attach it to each of the bases. It's only true if we're multiplying or dividing, which we'll see. Okay. So same idea. If you have a fraction inside, so a over b to the power of m, as long as we're multiplying or dividing, we can bring that power inside. So this is the same as a to the power of m over b to the power of m. Right? More likely scenario is that we have something like this, right? And we want to rewrite it as something like this. So probably for 5 and 6, we'll most likely be working from here to here. But we have to be comfortable moving back and forth. So this is just an extension of rule number 5. Seven. A to the power of 0, we've seen this before, right? Anything to the power of 0 is 1. It's a tricky one. Anything times 0 is 0. Anything to the power of 0 is 1. This is just a fact. Eight. A to the power of negative n can be rewritten as 1 over a to the n. So negative power just means that it's going to get moved down into the denominator. Right? Or, again, more likely is we have something in the denominator that we want to move to the top, right? And we can move a to the n from the denominator to the numerator by saying, well, that's the same as a to the negative n. Right? Yeah.
So if you use the second example, a to the power 1 divided by a to the power n, you say a minus 1.
Say that again.
So if you use the second example of the first one we did,
This one.
this one,
Yeah.
this is like to put the minus sign on top.
When we're like, yeah. Well, if you just have 1 over a. Yes. Because that's 1 over a to the power of 1. 1 over a to the negative 1. Yeah, you keep it. Cool. All right, so that's a handy one, right? We're able to bring things from the numerator or from the denominator into the numerator. Right? I'll use the same structure. If we have a power in the denominator, I ran out of room. In the denominator, we can move it to the numerator by making the power negative. So that's going to be a pretty go-to move. We want to move something from down in the denominator up to the numerator. Great. Make the power negative. All right. The thick of things here. A to the power of 1 over n. Maybe you use this trick in high school, right? If you had to take the third root of something, right? It's that something to the power of 1 over 3. Right? In general, you have a to the 1 over n is the same as the nth root of a. So Here I'll just say we can rewrite a root, right, as a power. Okay. So we can rewrite a root, or the nth root, I'll say. The nth root as a power. Okay. So if you have the fourth root of a, right, you would write that as a to the 1 over 4. Just a little mini example. The fourth root of a. The fourth root is indicated by, we put the little number in the hook, right? We're used to the square root. That's just the second root. And we don't even write the 2, right? But for any other power, we're going to write the number in the hook there. So the fourth root of a is the same as a to the 1 over 4. And that's a nice trick for your calculator too, right? If you have to take the 20th root of something, you just take that something to the power of 1 over 20. Not sure when you ever would, but if you had to, you can. Yeah. And so the same idea is if you have a to the power of m over n, right? We'll go through the motions here. So you have m in the numerator and n in the denominator of your power, right? So that's going to be the same. We can rewrite this, kind of unraveling it as a to the power of m to the 1 over n, right? Just separating out, m over n is the same as m times 1 over n, right? And then we can use fact whatever, where we can, right, pull out one of the powers, put it outside. Okay. And so what this becomes, right, and then a to the m to the power of 1 over n, that's the same as the nth root of a to the m. Yeah, it's a pickle. Let's see here. I'll just finish here. So it's an extension of rule number 9, but we'll look at it in more detail. Okay. So just to explain what's going on here, we can rewrite m over n as m times 1 over n. Right? So really what we have is a to the power of m times 1 over n. Okay. So then by rule number, this looks, yeah, 1 over n. Okay, so then that looks the same as this, right? Where we have the same scenario, a to the power of m times 1 over n. So we can rewrite it, we can go back and we can say that's the same as a to the power of m, and then all that is to the power of 1 over n. Okay. And so this we can rewrite. This becomes a to the m in brackets to the 1 over n by rule number 4, I think it was. Yeah. Bless you. So now you have a to the power of m inside the brackets. What if you just treat a to the m as the base, right? So just say, you could replace it with a b, and then it would be easier to look at, right? But a to the power of m is now going to be kind of like your base, right? Your base to the power of 1 over n, that's the same as the nth root of a to the power of n. Right? So this becomes the nth root of a to the power of m by rule number 9. What if I wanted you to say, I guess just rewrite a to the 4 over 3, right? So just rewrite it as a square root. A to the 4 over 3, we can rewrite as a to the power of 4 times 1 over 3. Right? That's going to be the same as a to the power of 4 to the power of 1 over 3. Right? We can swap out that power of 1 over 3 by a third root. But as far as work goes, right, this is what's happening in your brain. Right? But if you go from a to the 4 over 3 to the third root of a to the 4, that's good. Right, that's all you need to do. Okay. All the other stuff is just to show you how it works. Okay. So, how about a to the 201 out of 17? Just in one step. Really, we can look at this and say, well, whatever's in the bottom there, the 17, that's our root, right? And then the other stuff goes inside, right? If you look at the pattern, right, not so much the math behind it, you'll see that you have the 17th root of a to the 201, right? So that's what I want you to be comfortable moving around to, right? And vice versa. So what if I had the 20th root of a to the 4? That can be rewritten as a to the 4 divided by 20. Right? Any questions about that one? Could probably use some practice, right? But you'll get there. Okay. All right. You'll be glad to know that's the end of the power rules, right? Exponents. Let's do a little example. Example 117. If I asked you to simplify a to the 4 times a to the 8 over a to the 7. There's a couple of approaches that we could be doing because we're multiplying and dividing, right? No addition or subtraction. Right? So, okay. I think I want to bring my a to the 7 to the numerator. Right? So this is the same. I'll just rewrite it here. A to the 4 times a to the 8 over a to the 7. I can rewrite, and it would be equivalent if I wrote a to the 4 times a to the 8 times a to the... Thanks, guys. Oh. We only had a rule for adding the powers of two bases, right? But because these bases are all the same, we could have 50 of them in a row and we could just add all the powers, smush them all together, right? So this is going to be the same as a to the power of 4 plus 8, but minus 7. Technically plus negative 7, if you want to get picky. Yeah, sure. Plus negative 7. Yeah. We're going to continue. So we get, nice. That would probably be my go-to move, right? We could have simplified the numerator and said, well, a to the 4 times a to the 8, that's the same as a to the power of 4 plus 8, right, 12. And then bring the a to the negative 7 up top, 12 minus 7. But I like to just get everything on the same playing field and then smush them all together. Often it's easier, right? A little bit less work. Whew. Okay, you're doing great. How about example 118? If you had to simplify 1 plus I, don't freeze up. I know a lot of you went, ew. 1 plus I to the 3 times 1 plus I to the power of 9 over 1 plus I to the power of 6. These are all still the same bases, right? 1 plus I. So you can just look at it and say, okay, 1 plus I, that's one thing, right? And so you don't have to get freaked out by the 1 plus I. You can just treat it as one thing because it's recurring, right? 1 plus I, 1 plus I, 1 plus I. Yeah. So here's my little rant. It might be tempting to just pull the powers inside, right? Put the 6 on it, right? But that's not true. That's illegal math. What? Show me. You got it. So just as a note, it might be tempting to pull the powers inside the brackets. To pull the powers inside the brackets but that is only legal for multiplication and division inside. For multiplication and division inside. Yeah. For example, right, 1 plus I to the power of 3, right, that is 1 plus I to the power of 3, just going by the rules that we just developed, right? That's the same as 1 plus I times 1 plus I times 1 plus I. Phew. Got rid of the power, right? Just expanded it, okay? But now, because of our expanding that we know, right, we're gonna work through this and we're gonna say, well, that's the same as dealing with the first two brackets. I get 1 times I is 1, plus 1 times I is I, plus I times 1 is I, plus I times I is I squared, still times 1 plus I. That's okay, just hang tight. Right, because how do we expand? So what I'm doing is that like the FOIL? So here, right? What we do if we have more than two, right? You start with the two, ignore the last one. So expand by using the FOIL. And then we get this one, and then you can FOIL it to the second one, or the third one. Right, so here, 1 times 1 is 1. 1 times I is I. I times 1 is I. 1 or I times I is I squared. Now we're going to do the same thing again, right? 1 times 1 is 1. 1 times I is I. I times 1 is I. I times I is I squared. I times 1 is I. I times I is I squared. I squared times 1 is I squared. I squared times I is I to the 3. Whew. Just hang tight. It does it? I'm glad. Okay, so this is going to be the same as 1 times 1 is 1. 1 times I is I. I times 1 is I. I times I is I squared. Plus I times 1 is I. I times I is I squared. I squared times 1 is I squared. Plus I squared times I is I to the 3. Yeah. No, I didn't. You jokers. Man, oh man. No, you won't have to do this on the test. I'm just showing you why you can't just pull in the powers. So just be convinced after this. Okay. Okay. So now we can collect like terms and say that there's only one. Okay. How many i's to the power of 1 do we have? We have 1, 2, 3. So we have 3i plus 3i squared plus I to the 3. Okay. Are you convinced? Are you convinced that 1 plus I to the power of 3 does not equal, or sorry, 1 to the power of 3? I think we're all convinced, right? Because this is what I see a lot of for illegal math. They say, oh, okay, well, all I need to do is I just need to bring it in for it. Right? But we just showed that that's not true, right? And so you can't just bring in the power if you're adding or subtracting inside the brackets. It only works if you're multiplying or dividing, okay? But it works if you're multiplying and dividing, right? Okay. So just be careful. This, I'll do it in red, is illegal math. Right? If you tried to do something like that. We can only pull in the power if we are multiplying or dividing inside the brackets. Inside the brackets. Okay. Let's do our actual problem. Let's try to simplify this thing, right? But we're just going to treat 1 plus I as the base. Okay? So we can simplify by treating, oops, 1 plus I as the base. So we started with 1 plus I to the power of 3 times 1 plus I to the power of 9. So 1 plus I to the power of 3 was pretty nasty, right, if you had to expand it, right? Imagine 1 plus I to the power of 9. Yowzas. We don't have to. 1 plus I to the power of 6. So treating the 1 plus I as the base makes it a little bit easier, right? Because then they just hang together, right? And then I just apply the same principle as I did before, where I like to bring the stuff in the denominator up to the top so that we're working on the same level, right? So we can rewrite this as 1 plus I to the power of 3 times 1 plus I to the power of 9 times 1 plus I to the power of negative 6. Should make that clear. Right? But you have to be careful when you're bringing it up, right? Make it negative, because it's going to make a big difference. Big difference. Because we're subtracting. Oh, I'll wait for some giggles. No worries. Our common base, right, was 1 plus I. So if we're going to combine all these powers, right, we just add them up. So we have 1 plus I to the power of 3 plus 9 plus negative 6. If you went straight to minus 6, that's fine by me, right? I'm just showing you that we're doing the same thing. Right. Yeah. Which is the same as just 9 minus 6, right? But technically plus minus 6. Great. Which is what? To the power of, yeah, 6, right? Woof. We did it. Okay. Any questions about that one? Although it was kind of me convincing you not to bring in the powers if you're adding or subtracting inside too. So hopefully you're all convinced. How about example 120, where you have to simplify double brackets x plus 3 to the power of 5 to the power of 3 over 2. That's a big mama. Okay. We're not going to bring in the 5 on the x plus 3, right? We'll show the work though. So I'll just rewrite it here. I'm starting at x plus 3 to the power of 5 to the power of 3 over 2. Okay. How do we want to shake this down? Right. We can say that, okay, well, if I wanted to, right, x plus 3, that's our base. So we just treat it as one thing, right? This times this, right? We can ditch these brackets by saying, well, x plus 3 to the power of 5 times 3 over 2, right? By rule, whatever, I can't remember. You don't have to remember the rule numbers. You have to remember the rules. Okay. So we have, that's the same as x plus 3 to the power of 5 times 3 over 2. Okay, I have it here. I found it. Rule number 4. If you're curious. But if you're convinced, we can just take it. So we can rewrite that. We can, right? We know how to deal with fractions in general, right? 5 times 3 over 2, that's the same as 5 times 3 over 2. Right? So if we're multiplying or dividing, it doesn't matter the order that we do it. Right? And so this is the same as x plus 3 to the power of 15 over 2. And now we know that if we have a fraction in our power, right, the denominator of that fraction is going to be our root. Everything else goes inside, right? So this becomes the square root. I mean, technically it's the second root, right? But we're familiar with the square root of x plus 3 to the power of 15. Rule number 10. Yeah. So you don't have to have that 2 in the hook. It's just the square root. But technically, I guess it's there. Okay. Any questions so far? So if you've dealt with roots, you know that we use roots to kind of undo powers, right? It's if you have a power, then if you want to get it down to just the nitty gritty, right? So if you have x squared and you want to solve for x, then you take the square root of it and things go away, right? So adding, subtracting, right, undo each other, multiplying, dividing, they undo each other, roots undo powers. Okay. So we use roots to undo powers. Example, solve x to the 5 equals, I don't know, 15 for x. Okay. So if you had to do this, I think what you would do, right, is you would say, and I'm starting with x to the 5 is 15. Okay. If I take the 5th root of both sides, just like before, what you do to one side, you have to do to the other. It cancels the 5th power. Right, so now you have x is the 5th root of 15. So just like if you had something being added on one side and you want to move it to the other side, right, you have to subtract it from both sides. Whatever you do to one side, you have to do to the other, right? So x to the 5, if you're solving for x, you want to get x on its own, right? Then you have to take the 5th root to undo it. How does it come undone, you say? All right, challenge accepted. We can rewrite this as x to the power of 5 over 5, right? X to the power of 5 over 5, 5 over 5 is 1. That's the same as x to the 1, which is just x. Okay. But as long as you're convinced, right, that taking the root of something, right, is going to make the power go away, that's fine, as long as you do it to both sides, right? So there's no fifth power on your calculator, right? But we can say that x is the same as 15 to the 1 over 5, which you can do on your calculator. I'll show you. To use your calculator, to find 15 to the 1 over 5, okay, you're going to use the y to the x button. Okay, there's a square root of x button, but that's pretty pointless. We want the fifth root, right? And so you're going to punch in 15 on your calculator, and then hit the y to the x button. Okay. Just takes whatever's on the screen, and now you're working up in the power. You have to enter the power, and because we have a fraction here, I would use brackets. So first bracket, and then 1, and then divided by 5, of course. Close those brackets. So 1 divided by 5, end brackets. It's going to show you just 0.2. That's 1 over 5, right? So it's just showing you, hey, here's what I have in the power. So it's not until you hit equals that you get 1.718771928. Make sure that that's what you're getting, right? If you're just stuck in 2 decimal places, we have to fix that, right? But I think we should all be good now. Okay. So now, you know that x is 1.718771928. Phew, what a relief. Okay. So x is 1.718771928. Fair enough. Okay. But another example. Example 121. Solve x times y squared equals x squared minus y squared for y. Keeping in mind, right, that now we have 2 bases, x and y. Okay. So we're going to have, I'm just going to rewrite what we're working with here. Oh, I'll put it in the middle of the page. Xy squared is x squared minus y squared. If we're solving for y, we want to start migrating all the y's over to one side and do what we can about moving the x's to the other side, right? And so we're going to say, okay, well, that's the same as xy squared plus y squared equals x squared. Well, the x times y squared, that x is attached to the y, right? So we can't move it quite yet. Okay. So move y's to one side. Okay. We can pull out a common multiple, right, of y squared on the left-hand side. So then we have y squared times x plus 1 is x squared. Pull out common y squared. Right? Because if you expand this, you're going to end up at the same thing. You don't want to forget about this plus one. Right? Y squared times x. Y squared. All right. So we're closer to shaking out our y, right? Because now we can divide both sides by x plus 1, right? So we get y squared is x squared over x plus 1. This x got a little fancy. Divide both sides by x plus 1. Okay, we want to solve for y. We've got y squared. We know that if we take the square root of y squared, we get y, right? And then, but we have to take the square root of everything on the other side as well. Okay. So we can take the square root of y squared is the square root of x squared over x plus 1. I don't need those brackets in the denominator. Everyone's on board? Sure. Everyone's ready to be convinced. Fair enough. Okay. One little nitpicky thing that won't matter in this course, right? But if we take the square root, or in fact, if we square something, we lose the negative. So when we take the square root, we're back to either positive or negative values. So we just have plus minus there, but just be convinced, okay? Yeah. Because we want to solve for y, right? The whole goal is to solve for y. Y squared is x squared over x plus 1, but y isn't going to be x squared over x plus 1. So the square root of x squared over x plus 1. Okay. Everyone's ready to be convinced. Okay. So the square root cancels the square, right? The power of 2. So now we have that y is plus minus. Like I said, that one, I would be saying something false if I didn't put it in there, but I don't want you to worry too much about it. Okay. It's just because we lose negatives when we square something, right? Square something, it's always positive. Mind blown, I know. Okay. Oh, you want to simplify a little bit more? Yeah, sure, you got it. Can we simplify this even more? Oh yeah, you bet. Y is just putting the plus minus in there. Okay. We can rewrite this, right, as x squared over x plus 1 to the power of 1/2. Right, it's all under the square root. Okay. And just treating x squared and x plus 1 as two different bases, right? We can pull in the 1/2, the power of 1/2 onto each of those, right? Because you're dividing, right? So this is the same as y is plus minus x squared times 1/2 over x plus 1, treating x plus 1 again as one thing, right? One base to the power of 1/2. Okay. Whew. So y then must be plus minus x squared times 1 over 2. We're just left with x. And we can rewrite if we wanted to, or if you wanted to leave x plus 1 to the power of 1 over 2, that's fine. I like the square root of x plus 1. Now it's simplified. Yeah. Say when. Here. Yeah. Which one are you at? This one? Yeah. Okay. Wouldn't the power by the square root? Yeah. Yeah. But we're working towards that slowly but surely here. Because it wouldn't just attach to the x squared, right? It would also attach to the x plus 1, right? The square root. Okay. But we solved for y. Does that feel good or what? We have solved for y. Y factorial? No. Do you guys know factorials? 5 factorial. Factorial is an exclamation mark. 5 factorial is 5 times 4 times 3 times 2 times 1. 5. It's pretty fun. Okay. So that's all fine and good. So roots undo powers. What if we had to solve for something that's in the power? Okay. So what if we have to solve 7 to the power of x for x? How do we reach that power? Okay. Yeah. A little bit of magic. Income logarithms. Okay. Exponents and logs should sound vaguely familiar. I don't know when they do that, but at some point you've probably heard of exponents, which we just dealt with, and logs. Right. So logarithms, or logs if you want. If we need to solve for a value in the power, we will need to use logarithms. And what's so funny about logarithms is now they're no big deal, but when I was, going to school and whatever, and I was doing my math degree, my grandpa would always say, "Oh, like logarithms and stuff." Like, yeah, sure thing. Because now they're no big deal. They used to be very computationally kind of intense, but now we just have a log button and we don't care about it anymore, right? But it used to be a big deal to have to deal with logarithms. Now it's not. Okay? So call your grandparents. Okay? So logs can have multiple bases, right? Or different bases, I should say, right? We will only deal with log base e, right? The natural logarithm. Okay, so I'll call it log, but we'll only ever use the natural logarithm. In fact, it doesn't matter which one we use, okay? But for our case, we're just going to use the natural log, okay? Just because it's easier to, well, it's one button on the calculator, so that's why. Okay. So logs can have any base I don't know. I don't think so. Any positive base, I guess. Couldn't tell you. I can look it up for you if you want. But I suspect you don't care. So most common bases are base 10 and base e. E is like pi, right? It's just a number. E is roughly 2.71828. Yeah. Just a fact. It's on your calculator. If you want e to the x, oops, you want to have 1 and then e to the x. But we'll look at how to deal with e later, right? For now, just know that it's a number. Okay? And it's roughly 2.7. Okay? So we will work exclusively in log base e, which we write like this, log base e, okay, also called the natural logarithm. Denoted by ln, lowercase l, lowercase n. I'll make that more clear. Or when I write it, it just ends up being something like this. ln scribble. Okay. So just like exponents, right, we're going to develop all these log laws. Log laws, fun to say, fun to memorize. Yeah. Okay. We'll develop them just for the natural logarithms, but of course they apply to all logs. So all logs behave the same way. We're just going to narrow it down to just ln, the natural logarithm. Okay. Even though we are talking about ln, I think in high school they call it ln. I'll just call it log. So, because it's the only log that I'll ever need. Okay. So, all of the log laws we are about to develop apply to any base but we will show ln. the natural log. Log laws. So just log facts. Okay. Again, we see this kind of now sort of familiar notation. A and B are in the set of positive real numbers, meaning just A and B must be positive. There you have it. Okay. Just in general, for the rules that we're about to develop, A and B have to be positive. The first rule, and the rule that we're going to use a lot, is that the log of A to the power of B, we can conveniently bring the power down, bring the B down, and it multiplies it in front, right? And they'll be equivalent. Okay? So this is the same as B times the log of A. That's nice, because how else would we bring down that power that we're trying to solve for? Right? So if you're trying to solve for B, you want to be able to shake it out of there. You take the log of something, A to the B, and then that'll let you move the power down in front and multiply the log A. Okay. So that's a handy one. Very similar, if you have something like the log of A to the negative B, that's the same as negative B times log A. Right, very similar. A to the negative B is the same as 1 over A to the B, right? But that you can rewrite as negative B times log A. Okay. If you see something that you can write as the log of A times B, you can break those up, A and B up, by adding the logs. So the log of A plus the log of B. So if they're multiplied inside the log, if you want to break them up, then you can add the two individually, the log of A plus the log of B. Okay. Similar idea, if you have the log of A divided by B, that's going to be the same as the log of A minus the log of B. Right, so if you have division inside, then you're going to subtract the the denominator from the numerator, essentially. And that's it for the log laws, which are also not on your formula sheet. How rude. So I expect you to know those. Let's do an example to see what's going on here. So if you have 4 equals 3 to the x, and I ask you to solve for x, now you see the x is in the power, so how are you going to get at it? You have to take the log, right? And so just rewriting it here, 4 is 3 to the x. I can take the log of both sides. So the log of 4 is the log of 3 to the x. Right? Take log of both sides. Now, log of 4, we're just going to leave it for a little bit, right? We're trying to shake out that x. We know by the log laws, we can bring the x down in front and it would be equivalent. So this is the same as x times the log of 3. And the log of 4 just stayed over here. So now, to solve for x, we can divide both sides by the log of 3. So x is the log of 4 divided by the log of 3. Oh, I switcherooed. I like to have my x on the left side. I did. It's kind of a go-to move of mine. I move the x to the other side. Because you divide both sides by the log of 3, right? Just the, because what I want you to imagine, right, is you're holding this x steady because you want to solve for it, so that everything else gets moved to this side. But then, because I like to finish with my x on the left. Okay, I'm there now. And we're not going to simplify that. That's simplified enough. Okay. All right. How about, what if I asked you to solve without knowing what these variables are, right? F equals P times 1 plus I to the power of n for n. We don't know what F or P or I or n are. Doesn't matter. We can still solve for n. Okay. So if you have to solve this for n, okay, what are we going to do? We want to try to get n on its own. N is attached to the 1 plus I, right? But the p is multiplying that. So we have to move the p over to the left-hand side first. So just rewriting here. F is p times 1 plus I to the n. Moving the p over to the left-hand side. Oops, threw an r in there. That'll throw you for a loop. F divided by p is 1 plus I to the power of n. Okay. Okay. So now I can put the logs on here, right? I can log both sides to get the log of F over P is the log of 1 plus I, oops, 1 plus I to the power of n. Treating that 1 plus I as just a base. Right? I'll leave the left-hand side for a while. The log of F over P, we'll just write it out, is n times the log of 1 plus I. Bless you. So trying to solve for n, right, we're going to divide both sides by the log of 1 plus I. So I'm doing my signature move here. N is the log of F over P over the log of 1 plus I. Done. Because there's nothing really, we could work with the log of F over P, but we're not gonna. Yeah. That was tricky because we're not really comfortable working with just variables. That's okay. How about solve 5 equals 4 to the x for x. We're going to end up with one nice number. Well, not nice, but a number. So 5 equals 4 to the x. We can take the log of both sides to bring that x down, right? So we can work with it. So the log of 5 is, how do you guys feel about going straight to the x times log of 4? Okay. Yeah, because I'm taking the log of both sides, so I'm taking the log of 4 to the x, which I could write out as one step, and then the next step would be to bring that x power down in front, right? But we know the goal of this is to bring the power down, so we know how it's going to unfold, right? So that's why we can just write x times log 4. Solving for x, signature move, x is the log of 5 over the log of 4. Log of 5, right? On your calculator, you're going to have 5 on the screen. Okay. And then there's an LN button. So working up from the bottom left-hand corner, we've got the C, the recall, the store button, and then the log button, the LN button. Okay. So what you're going to do is you're going to have the number that you want to take the log of on the screen, so 5, and then hit the log. Okay. So I'll write it down here. The log of 5 is 1.609437912. I'll write a little note how we use our calculator. Okay. But the log of 4 is 1.386294361. And a couple of ways that we could do it. You could just enter it as a stream on your calculator. It knows how to do it. Okay. I'll hold off on showing you how to do it. Okay. But we're going to have 1.6094. I'll just type it in. 1.609437912 divided by 1.386294361. I'll show you how to store stuff on your calculator probably next day, but I want you fresh for it. So x is going to be 1.160964047. Okay. I'll do a little note here. To find the log of 5 on your calculator, you first have to hit the 5, okay, and then hit your LN button. And I think it just does it. And that's it. Or to do log 5 over log 4, okay, you're going to hit 5, then ln, then divided by 4. Throw little buttons around there. ln, and then equals divided by 4 ln equals. The equals is going to give you the answer, right? Otherwise, it'll just show you the log of 4, the last thing that it did. Okay. So you can just do it as a stream. Okay. Example 128. Solve 3 plus y to the power of x equals 34 for x. You guessed it. So we have 3 plus y to the power of x is 34. So 3 plus y, that's all to the power of x. So we can go straight to just taking the log of both sides to bring the x down. Okay. So we get x times the log of 3 plus y is, the log of 34. Okay. So x, dividing both sides by the log of 3 plus y, we get the log of 34 over the log of 3 plus y. And that's simplified. We can't simplify further since we don't know why. We don't know why. Okay. Enough rules for today, maybe? So make sure that you do practice problems. There's suggested problems at the end of 4.1. Okay. Or even throughout 4.1. Make sure you do those for practice. They're not due just for practice. See you guys on Monday? Weird. Oh, yeah. Yeah, if you didn't get your test, come grab it. And I think you have an assignment due.